Alright, so we're going to look at this example here. Is the crown gold? So legend has it Archimedes was asked by King Hero of Syracuse to determine whether a crown of pure gold, was pure gold, or had been adulterated with the lesser material by an unscrupulous goldsmith. Oh, sorry if you heard my dog. It was this problem that led him to the principle that bears his name, Archimedes Principle. In a modern version of his method, a crown weighing 8.3 newtons is suspended underwater from a string. The tension in the string is measured to be 7.81 newtons. Is the crown pure gold? Alright, so the idea here, if we're drawing a quick sketch, alright, is we have some sort of container or basin, and in that basin we've got, it's like water. Come on. Alright, so we'll just kind of draw a little bit of blue here for water. And we've got a string that hangs down, and attached to that string, of course, is a crown. Oh, beautiful. Alright, so that's kind of what we've got going on. Listing what we know, looking at the prompt, well, a lot of it's just kind of fluff. But we're told that we have a crown that weighs 8.3 newtons, and we're told that the tension in the string is 7.81 newtons. All right, we'll weigh 8.3 newtons. We know weight is the force of gravity. So we know the force of gravity is 8.30 newtons. We're also told that tension, force of tension, is 7.81 newtons. And let's see, anything else we know? Well, we know that we're dealing with water, and since we're dealing with fluid principles here, we probably will need the density of water. All right, so that's 1,000 kilogram per meter cubed. And looking for what we're trying to figure out, right? We're trying to figure out, is the crown pure gold? All right. Well, how do we quantify that? Well, thinking about gold, well, we could say, oh, well, we could figure out if it's gold if we figured out the density. So we're going to figure out the density of this crown. Right now it's a question mark, and if that happens to be the density of gold, which, kind of off to the side here, density of gold, if we look that up in a table, that's 19,300 kilogram per meter cubed. So we'll compare this number to this number and see if it's gold or not. Right? If it's either more or less dense, then there's going to be some other material there that's making it so the crown's not pure gold, right? Which could be a good thing, but I guess it's not what this king is looking for. All right, so where do we go from here? All right. Well, let's draw another diagram, a free body diagram. So I'll draw a die here that represents the crown, and the crown here is suspended. It's in equilibrium. All right, so looking at the forces acting on this crown, we've got the force of gravity, we've got tension, but since it's submerged underwater, we also have a buoyant force. All right, so we've got the force of gravity straight down, and then we have tension and the buoyant force upward, straight upward. And both these will have to sum in such a way that it's in equilibrium. So if we're applying Newton's second law, right, some of the forces in, let's say the upwards is positive y, in our y direction, that sum is going to equal to 0. So our force of gravity is going to equal the buoyant force plus tension. All right, so how is this helpful? Well, we know a formula for the buoyant force, right? We can replace that with rho v g. Let's be particular with our subscripts here. This is the weight, so the buoyant force is equal to the weight of the fluid displaced by the object we're analyzing. So the object we're analyzing here is the crown, and the fluid displaced is water. So it's the density of water times the volume of the fluid displaced. Well, since the crown is completely underwater, it's going to be the volume of the crown, right? So you can write that as volume of water, but then you can just replace it with volume of the crown. So I'm just going to do that in this step right here. So I'm just going to rewrite this. This is the density of water times the volume of the crown times acceleration due to gravity plus tension. All right, so kind of looking at this right off the bat, we know the force of gravity, that's a known value. We know tension, that's a known value. We know density of water, G is the only thing we don't know is the density, or excuse me, the volume of the crown. And we want to get in our equation the density of the crown. Well, as a quick aside, all right, well, we know that the density of the crown is just going to be the mass of the crown divided by the volume of the crown. All right. So we could rearrange for that. I'm going to do a little bit of a math trick right here. All right. It's kind of up to you whether you want to use it or not, but I'm going to multiply by 1. In particular, I'm going to multiply by 1 as G over G. All right, I'm allowed to do that. I'm allowed to multiply by 1. Why am I doing this? Well, you see our numerator has now turned into the weight of the crown. And we divide that by the volume of the crown times G. So we have found an expression for the volume crown in terms of the weight of the crown. And that's useful just because it's a little less math, because I know the weight of the crown, but I could have just used the mass of the crown and rearranged and solved. But anyway, so let's see. So where are we now? So scroll here. So we've got that the weight of the crown minus tension is equal to the density of water times the volume of the crown, which we just found to be weight of the crown divided by density of the crown times G. All this times G plus tension. Ooh, so maybe now you might see another reason why I did this. The accelerations cancel out. So we're left with density of water divided by density of the crown times the crown's weight plus tension is all equal to the force of gravity. I didn't write this correctly, did I? I shouldn't have had this extra tension term, right? Because I moved it over to the other side. All right, sorry about that. It's literally like 5 a.m. right now. Okay, so then we have that the density of the crown, so rearranging here, is going to be density of water, force of gravity, divided by force of gravity minus tension. These are all known quantities we can plug in that we have above. I'm going to save you the agony of that step, leading us to rounding to a couple sig figs here, about 1,700 kilogram per meter cubed. Right? I don't need to be super precise about this because we're just comparing it to the density of gold, where we said the density of gold was 19,300 kilogram per meter cubed. So this is not pure gold. So it looks like King Hero would not be very happy with us. Or better said, whoever made the crown.